Hello and welcome to my video about Calderbank-Shor-Steane codes. These codes form a class of quantum error correction codes that use classical error correction codes to construct a quantum code that can correct quantum errors. To understand these kind of codes, we first need to understand the basics of classical error correction codes. So we begin with this. More precisely, we need to understand linear classical codes. These codes work as follows. So the notation is that an nk code, denoted C, encodes k bits into n bits. And of course, n is larger than k. The resulting code contains of 2 to the power of k code words of length n. And such a code can be defined by defining its generator matrix. This is an n times k matrix that maps messages x to code words y. So a code word is given by the matrix G applied to the message vector x. Let's look at an example. The so-called 3-1 repetition code is a 3-1 code, as the name suggests, so it encodes 1 bit into 3 bits. And it does this simply by encoding 1 bit into 3 repetitions of the bit. So the code words are, for the message bit 0, simply a vector of 3 zeros, and for the message bit 1, a vector of 3 ones. The generator matrix for these code words is then simply given by simply 3 ones in a column. You can quickly verify this by applying the matrix G to the two 1-bit messages 0 and 1. A different way of defining a linear classical code is by using parity check matrices. These will be very useful when it comes to detecting and correcting errors. So, in terms of a parity check matrix, an nk code consists of all vectors x of length n, such that the matrix H applied to a vector x equals 0. So here x are the code words. Don't confuse it. Before, x was the message. And H is called the parity check matrix. It is an n minus k times n matrix. And we can construct this matrix from the generator matrix of the code. You simply have to pick n minus k linearly independent vectors orthogonal to the columns of G. The reason why it works this way is that the columns of G span the space of code words of the code. Let's look at the example we had, the 3-1 repetition code, and see how we can construct the parity check matrix for this code. So remember, the generator matrix was simply given by 1 column of all ones. So now we need n minus k, which is 3 minus 1, which equals 2 in our case, orthogonal vectors to this column of ones. And you can easily verify that the following matrix consists only of vectors which are orthogonal to this column. And what you can also quickly verify is that the vectors that fulfill this parity check matrix condition, H applied to x equals 0, those are the columns with all ones and the columns with all zeros. And this means these two vectors are the code words of the code, which coincides with the code words that we got from the generator matrix definition. So these two descriptions give an equal set of code words. Okay, but how does it work to detect errors using these codes? So remember, a code word is given by applying the generator matrix to the message, and for every code word, applying the parity matrix to the code word equals 0. Now, if an error occurs, we denote errors by E. This is simply an n-bit string that has ones whenever an error occurs and zeros when there's no error. So If an error occurs, we get a corrupted code word. We denote this y prime, and this is simply y plus e. In this case, if we apply the parity check matrix to the corrupted code word, what we get is the sum of h applied to y plus h applied to the error string e. And since h times y equals 0, what is left is h times the error bit string e. And that's why we call this expression he the error syndrome. If it is 0, we know that no error has occurred. But if it is greater than 0, we know that there's an error. And actually, from this error syndrome, we can even see where the error has occurred. So let's again work in the example of the 3-1 repetition code and see how we can detect errors here. Here, 3 types of 1-bit errors can happen. So we can have bit flips either in the first bit, in the second bit, or in the third bit. So we have 3 different kinds of error vectors. The corresponding error syndromes, which you can easily verify, are for the bit flip in the first bit, the error syndrome is the vector 1, 0. If the bit flip happens in the second bit, the error vector is 0, 1. And if the bit flip happens in the third bit, the error syndrome is 1, 1. So if we obtain an error syndrome, we can directly see at which bit the error has occurred. And then we can simply correct the error by flipping the bit again. But what happens if we have 2 errors? So suppose we have an error in the first bit and another error in the second bit. If we calculate the error syndrome for this error vector, then we will see that the syndrome is the vector 0, 1, which is equal to the syndrome for the error vector e2, where the bit flip only happened in the second bit. So this kind of error correction code can only correct 1 bit error, not 2 or 3 errors. But in general, there are linear classical codes that can detect more than 1 error, of course. And we usually use the Hamming distance to see how many errors it can occur. So the Hamming distance of 2 bit strings is the number of positions in which the 2 bit strings differ. So if I have a vector with 3 zeros and a vector with 3 ones, then the Hamming distance would be 3. And the distance of a code is defined as the minimum Hamming distance between any of the code words, which are of course not the same. So the Hamming distance of a code word with itself is always 0, so we exclude these cases. Then a code with Hamming distance 2 times t plus 1 can correct up to t errors. And this works simply by choosing the unique code word such that the Hamming distance is less or equal to t. Or in other words, so that the Hamming distance between the corrupted code word y prime and the actual code word. So you simply choose the code word of your set of code words which minimizes the Hamming distance. And if the distance of the code is 2t plus 1 and up to t errors occur, then this code word that minimizes the Hamming distance is always unique. In the 3-1 repetition code example, the distance of the code was 3 because we had the 2 code words 0, 0, 0 and 1, 1, 1, and their distance is 3. So the code can correct up to 1 error, and this is what we have seen before. When there were 2 errors, it wasn't possible to find the unique code word that minimizes the Hamming distance. There is another concept that we have to introduce before we can go to quantum error correction, which is the concept of a dual code. So if you have an NK code C with generator matrix G and parity check matrix H, you can define the dual code, which is an n-k code C dual, where the generator matrix is the transpose of H and the parity check matrix is the transpose of G. Okay, now we come to quantum error correction. So we now want to define Calderbank-Shor-Steane codes using the definitions that we have given for classical linear codes. So the concept is the following. As an input, you use two classical codes, an NK1 code C1 and an NK2 code C2, where C2 is a subset of C1. And also, it is important that C1 and the dual code of C2 can correct up to T errors. The output of this procedure is then an NK1 minus K2 quantum code that we denote CSS C1 C2, which can correct up to T qubit errors. Let's see how this works. So the construction is as follows. For any code word of the code C1, we define the following quantum state. The state is labeled by x plus C1, and it is given by 1 over the square root of the cardinality of C2, which is the number of code words of C2, and then the sum over the states x plus y, where y is a code word in the code C2. Yeah, and the cardinality of C2 is in our case 2 to the power K2. It's important to note that different code words of C1 can lead to the same quantum state. Actually, when in the case where x minus x prime, where x and x prime are code words in C1, when the difference is an element of the code word C2, of the code C2, then the x and x prime lead to the same quantum states. This is why we have used coset notation here. If you're not familiar with cosets, it doesn't matter, it's not very important for this. Just a consequence of this is that the quantum state only depends on the coset in which x is in, and there are the cardinality of C1 divided by the cardinality of C2 cosets, which means that this is the number of code words in the quantum code that we get. And this is 2 to the power of K1 minus K2. Okay, so this is a quantum code. Therefore, we want to correct quantum errors. What kind of errors can occur when we deal with qubits? Of course, we can have bit flip errors. This is similar to the classical case. A bit flip error maps the vector 0 to the vector 1 and the vector 1 to the vector 0. We can also have phase errors. Here, the vector 0 remains unchanged, but 1 is mapped to minus 1. Note that the definition of these errors was made in the computational basis, but there is another basis for qubits that we can use. It is the Hadamard basis. It is also a basis of the qubit state space, and the connection to the computational basis is given on the right side. So the basis states are plus and minus, and they are simply linear combinations of computational basis states. In the Hadamard basis, the errors have a slightly different form. So here, bit flip errors happen in a way that the plus state is mapped to the plus state again. You can see this in the definition of the plus state on the right side. So a bit flip error would map 0 to 1 and 1 to 0, which doesn't change the state. But the minus state is mapped to minus the minus state. Because here, if you flip a 0 to a 1 and a 1 to a 0, you get minus the state. And phase errors have the form that plus is mapped to minus and minus is mapped to plus. So as you can see, compared to the computational basis and the Hadamard basis, bit flip errors take the form of phase errors in the computational basis, and phase errors in the Hadamard basis take the form of bit flip errors in the computational basis. This is an important observation that we will need later when we talk about how actually the code corrects errors. So keep that in mind. We can sum up bit flip errors in a way that if you have a vector x, then this is mapped to a vector x plus a string that contains all the bit flip errors. We call it e-bit. And phase errors have the form that a vector x is mapped to -1 to the power of x, the vector product of, so the dot product of the vector x with the vector e phase, which contains all the phase errors, times the vector x. Okay, this means that the corrupted code word has the form 1 over the square root of 2 to the power of k2, which is the cardinality of the code C2. And in the sum over all the vectors, we now have a factor, -1 to the power of x times e phase. And the vector is now labeled by x plus y plus the error vector for bit flip errors. Okay, so how do we correct errors? Let's start with bit flip errors. Here we use an ancilla state that is initially in the 0 state. And in this ancilla state, we store the error syndrome. So the error syndrome is given when we apply the parity matrix of the code C1 to the string x plus y plus e bit. And we store it in the ancilla state as by the definition of the parity check matrix, h1 applied to x is 0, h1 applied to y is 0, so the error syndrome is simply h1 times e bit. Then we measure this ancilla state and correct all the bit flip errors at those positions where we detected one. And the resulting state is this one. It is 1 over the square root of 2 to the power of k2. And the phase error vector has remained in the sum, but in the state we now only have x plus y, and the bit flip error string has disappeared because we have corrected it. Now we have to correct phase errors, and here the Hadamard transformation plays an important role because, as we have seen before, in the Hadamard basis, phase errors have the form of a bit flip error. And as we have just seen, bit flip errors are very easy to correct using simply the parity check matrix. So what we do is we apply a Hadamard transformation to the whole state. And the result is this term here on the right side. In the factor, we have now 1 over the square root of 2 to the power of k2 plus n. Then we have an additional sum now, which is over z prime. And z prime is an element of the space f to n, which is simply all the bit strings of n bits that there are. So all combinations that are possible. Then so the factor in the sum is now -1 to the power of x plus y times z prime. And the state is now z prime plus e phase. So the phase error is now in the quantum state and not in the -1 factor anymore. Which means that we can easily correct it by using a parity check matrix. But first, we simplify the form of the state on the right side by using the following identity. So the factor -1 to the power of y times z prime, when we sum over all the y's, this expression is either 0 if z prime is not an element of the dual code of C2, or it is 2 to the power of k2, which means the cardinality of C2, if z prime is an element of the dual code of C2. We don't prove this statement here because this goes beyond the scope of this video, but you can probably try to prove it your own, or find a source in the internet that shows you how to prove it. So if we use this, then we can simplify the expression above, and the resulting state is now 1 over the square root of 2 to the power of n minus k2. The sum now goes over all z prime in the dual code of C2 because all the other terms are 0. And in the sum we have -1 to the power of x times z prime and the state z prime plus e phase. Okay, now we need to correct the phase errors with the parity check matrix of the dual code of C2. because this is where the code words Z prime are from. And we do that and get this expression. Like, we use the same procedure as before. When we corrected the bit flip errors, we use an ancilla state, measure the error syndrome, and correct it. And the only thing that is now left is applying a Hadamard transformation again, because the Hadamard transformation is its own inverse. So we get from the space from the dual code of C2 back to the actual code. And as you can see, the resulting state after applying the Hadamard transformation is 1 over the square root of 2 to the power of k2, and the sum over the states x plus y, where y is from the code C2. This is exactly the state, the code word we started with. So by using the properties of the linear classical error correction code C1 and C2 dual, actually, we have corrected the quantum errors in our quantum state. And here you can see why C1 and C2 dual both need to be able to correct T errors, because then we can correct T bit flip errors and T phase errors. So the quantum code can actually correct T qubit errors. So yeah, this is how the Calderbank-Shor-Steane code works.